السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. إن شاء الله in the second half we'll focus more on how we can use language models in IR. But before that, let me walk you through an example just to make sure that you understood what we studied in the first part. Let's say that I have these words in the vocabulary. I have 4 words only. I have A, B, C, and D. Okay, let's say that we only have 4 words in our vocabulary. Okay, now what do I need if I want to build a unigram language model? What are the probabilities that I need? Just raise your hand, please, if you know. Toba? Okay. Yes. Probability of B, of C, and D. Okay, so that's unigram. How about bigram? Yes. Here. Okay. Probability of A and probability of B over what do you mean by over? A given A. Okay, there is no probability of B over A. Probability of B given A. Probability of C given B. So okay, let me make sure that you understand. This is not a text that I want to compute the probability for. These are just the vocabulary. Okay, so I have just four words in the vocabulary. Okay, I didn't get any query yet. I don't want to generate any to estimate any probability. I just want to see what are the parameters of the model. Okay. Again, you say A over B. You mean A given B? Okay. You didn't go with a pattern, so it's very hard that you are doing that. But let me say that you need probability of A and also B and C and D, right? So all of these probabilities are still needed. Okay. Probability of B given A, you can also see probability of B given C, probability of B given D, right? And here, probability of C given B, you can also say probability of C given A, probability of C given D, and here probability of A given B, you need also probability of A given C, probability of A given D, and so on, right? So you can also do this, D given A. Just 1 second. You want to answer? Yeah, go ahead. Huh? Why what? Yes, this is the language model. What do you mean? Sorry, I didn't get your question. Yes, this is C given D. Okay. This is not the text, Heb. This is just the vocabulary. These are the words in the vocabulary. We didn't have any text yet. We didn't have any query or something. That's just the vocabulary. All the words in the vocabulary, in the language. Okay. So P of D given A, P of D given B, right? P of, yes, Toba? Very good. Yes. This B given B, C given C, A given A, D given D. Did we cover everything? Cover everything? Okay, so you will see that this is 4 times 4, right? N squared, and this is 4. Yes. Mhm. They are needed also. Yeah. We are, yeah. Let me write them. Okay. Yes, they are needed, of course. So I'm saying that these are 4 because that's n. N is 4 here. So that's n and that's n squared. All of this are n squared. So to build a unigram language model over n words, we need n probabilities, right? N enters in the probability distribution. For a bigram, we need n plus n squared. For trigram, n plus n squared plus n cubed, and so on. Okay. Any question about this? Okay. Can one of you tell me now if I have 2 models, unigram and bigram over English. Okay. So English unigram model and before that, let me ask you another question. If I have this bigram model, so forget about the unigram model. I have this now, this bigram model, okay, and I want to generate text out of it. So language model has 2 ways of use. Okay, we can use it to generate text, and we can use it to estimate probabilities of generating, of observing text, of generating text. Okay? So if I want to generate text out of this, what should I do? Out of any language model. It's a probability distribution, right? So it's like we have a very long vector of probabilities, and we have here this the meaning of each. Okay, so that's probability of A, that's probability of A given C, that's probability of B given D, and so on. Okay, how can we generate text out of this language model? Let's say that I want to generate a sentence of 3 words. Bigram, yes. Yes.
We can pick one of the words at random at first.
At random. What do you mean by at random? Uniformly?
Yes.
Why should it be uniformly? We have these probabilities, right? We have these probabilities, right?
Yeah.
So the first word should be picked based on these 4 probabilities, right? Based on these 4 probabilities, I will pick one to start with. Okay, let's say that we picked C. So we generate C. How about the next one? It doesn't have to be the largest, right? Because we will select randomly, but of course the next word will depend on the probabilities. Okay? But which probabilities here we should use when we select the next word? Everything that is given C, right? So this one. Second row also, or yeah, no, not second row. This one. This one. And this one, right? So based on this probability distribution, we pick one randomly, not uniform, okay, based on these probabilities that we estimated. Okay. So let's say that we selected B. If we select randomly completely, what do you mean by randomly? Random mean, by the way, random doesn't always mean equally probable. Forget about the use of the word in our lives and when you use it in probabilities. Okay, when you select randomly using a probability distribution, then it's not uniform. It's based on the probabilities. Okay, yeah, for example, if the probabilities here for the unigram probabilities are 0.1, 0.5, 0.25, and that should be what? 0.15. Now I select one of these based on these probabilities. Okay, It doesn't mean that I will select the highest, of course. Okay? Randomly, I will choose one, but most probably, the highest probability to be chosen is B. That doesn't mean that I will choose B. It's random, right? But if I choose 100 times, okay, 10% will be A, 50% will be B. That's the meaning of the probability, right? Okay. So C, B, then how should I select the third one? Anything based given B, right? So which ones? This one, given C or B? Huh? Maybe C. Yeah. I'm trying to see where. So this one, and this one. Right. So this is the probability distribution. By the way, these four are probability distribution because all are given B. Then we'll select based on this probability. So maybe I select B again. Okay. Right. Now, can I estimate the probability of selecting this pattern? CBB? Yes, of course, using these probabilities. Right. So what would be the probability? Ihab, are you with us? What is the probability? Anoud, what is the probability in this case? Probability of generating CBB. Any idea? Amira? Probability of C times probability of B given C times probability of B given B. And all of that is in the language model. Right? I hope that this is now clear. Okay. Any question about this? Okay, now let's move on. Now, how can we use language models in IR? Okay, it should have been animated, but anyway, we'll do it that way. What is the idea here? We want to rank documents based on probability of D given Q. Why is that? Because we are given a query, right? And we want to estimate the probability that D is relevant given Q. You know that we can use Bayes rule, right? So Bayes rule, if you look at this is Bayes rule. Probability of D given Q is equal to probability of Q given D times probability of D divided by probability of Q. Right? So that's Bayes rule. Now let's look at every component of this and see what can we do with it? How can we estimate it? Or actually, do we need it? The first one is P of Q. What is the meaning of this? What is P of Q? Probability of the query. What does that mean? Yes, probability of getting the query from a user. The general probability of seeing that query among all possible queries. Okay? Right? That's the meaning of that. I said here that we should ignore. Why? Everything that's small than we should ignore? Why should we ignore any small probabilities?
Because
if
it will be constant.
Because it's constant. Constant where? For a given query. Yani, remember, we need to compute this for every query, right? Sorry, not for every query. For every document given a specific query. Okay? So given that query, this will be in the denominator of this for all. It will be the same. Whether it's small or not, it is the same. Okay? So it will not change the ranking, the relative ranking of the documents. Okay? So this one, we don't need to even estimate because it's constant across different documents. Now, what is this? probability of D, probability of observing this document. Okay? Usually we assume that this is equal for all documents in the collection. Okay? That's probability of the document being relevant given no query أصلا. Okay? What is the probability of a document to be relevant generally? We can assume that it's equal over all collection as long as we don't get any query, right? So it's not conditioned on any query. So we can assume that it's constant. And if that's the case, then we can also ignore, right? It's just a constant factor. But in reality, actually, sometimes we have some values for this. Okay, we call that prior. Sometimes there are some documents that are preferred than other. Okay, we will, inshallah, later we'll talk about something called page rank. Okay, page rank is an algorithm that gives a score for every document based on how this document is important and the quality of that document. Okay, regardless of any query. If that's the case, then we can use page rank as an estimate for that probability. But if we don't have that, we'll just ignore it. Okay? Yes. You can think of it that way. We will later get to that. Okay? But you can think of it that way. You can think of page rank as a score that will be high if the document is more important or has higher quality. Okay? Yeah, for example, page rank of CNN page is much higher than page rank of my page, because CNN is much more important than me. The page of CNN. How? Stay tuned for 4 or 5 weeks. Okay? We'll study it, inshallah. But for now, we can assume that P of Q is constant, and we'll just ignore it. What is left? P of Q given D. What is that probability? What is the meaning of that probability? That is the probability of generating the query from the document. That's what we are after. Okay? Type. Yeah, that means that we will ignore this one, and we will ignore this one. Does that mean that P of D given Q is equal to P of Q given D? No, it doesn't mean that, but it means that if we want to rank documents based on this probability, it's sufficient to rank documents based on this probability. It is the same rank, exactly. Just because P of D and P of Q is constant. Okay, so it will not change the relative ranking of documents. Yeah, Ihab. Okay. Any question about this? So what should be the next step then? Yeah, we will just focus on this now, right? Just focus on this. How to estimate it. Okay, so we attempt to model the query generation process. We rank documents by the probability that the query would be observed as a random sample from the respective document model. This is what we explained earlier, right? So the process that the user model here, as we mentioned earlier, the user has a document in mind, will try to pick words from that document. So we want to model that query generation process. We will rank the documents by the probability that this query would have been randomly sampled from that document. Okay. So we'll rank according to probability of Q given D. That's the message here. Okay. Now, usually we don't know the model, but we can estimate these probabilities based on the sample of the text of that document. Now let me explain this. each document is written by an author, right? There's someone who wrote this document. That person, before he or she writes the document, has a topic in mind, right? And based on that topic, he or she chosen some of the words to be in the document, right? So the actual model of the actual language model of the document is not the document itself, right? It's in the mind of the writer of that document. What we see in the document is actually a sample from that model. Because the writer actually has chosen some of the words. Yeah, for example, instead of saying capital of Egypt, he said Cairo. But he would have said capital of Egypt instead of Cairo. But he chosen to use Cairo, right? So he made some decisions, and these decisions is based on the language model that he has about the document that he wants to write. Okay? That's not the searcher, by the way, that's the writer of the document now. Why I'm saying that? Because I want to say that the model, we don't have the exact language model, but we will estimate it from the sample that we see. What is the sample that we see? The document, the words that appear in the document. Okay? That's what we want to estimate the model from. So we have a sample of the text that represent the model. And from that sample, we want to estimate the model itself, the language model. We're not talking about queries here. Okay, we're talking about documents now. Now this is the step where we want to build the language model itself for each document. Okay, are you with me now? Okay. Right. Now, given that sample, we want to estimate the language model. Then we compute when we have a query like this, we want to compute the probability of seeing that sequence given the model. Now, how to compute this probability? How to compute P of the query, generating the query from the model of the document. We will, using the unigram language model, we'll assume the conditional independence assumption. So, probability of the query given the language model is, of course, this is the query, this is the terms that appear in the query. We will assume that these terms are completely independent given that model. So this probability is equal to the multiplication of the individual probabilities. Probability of Qi, what is Qi? That's term I in the query given the language model of the document. Okay? Right. Now, this is called query likelihood model. This is called query likelihood model, or QLM. So query likelihood model, we assume that the query terms are independent or conditionally independent given the document language model. Now, what is remaining? What do we need to get now to compute this probability? We need to compute this, right? If we compute this for every query term, then we compute it for the query as a whole, right? So this is generally, if you think about the query as a whole now, every query can appear more than every query term might appear once or more, right? So just looking at this, if the term repeated, then it will be multiplied more than once, right? Actually, it will be multiplied TF, QI, and Q times. What is TF and QI and Q? That's the term frequency of that term in the query, which means how many times this term appears. Usually, of course, the query terms are all unique, right? Usually, there is no repetition, but just in case, if it happens that a query term appeared more than once, then it will be multiplied more than once, of course, which is captured here. Okay, so here these QIs are unique. Okay, so we didn't change much from that. These are equivalent, just accounting for the case that a query term might appear more than once in the query. Okay, yes. Unigram language model, yes, still, yes, and we will continue like that to the end. Okay, now we need to compute, we need to estimate this. If we estimate this, then we are done. Right? Is that clear? We have a query that has multiple words, although there is a sequence, but the assumption here is that we have a conditional independence. Okay, so these query terms are independent of each other. So instead of having the full query, we can decompose it into a multiplication like that. Okay, that's the unigram model or the conditional independence assumption. Now, if we compute the probability of observing each single query term given the model, we just multiply them and that's it. So this is what remains now. Now we need to estimate this probability. Usually the first thing to do when we need to estimate such probabilities is to use what we call maximum likelihood estimates, okay, which is the intuitive way that we did earlier in the lecture. If I want to compute probability of observing a term from the language model of the document, what I will do is to count how many times this term appeared in the document and divide by the number of the terms of document, which we call it the length of the document. Okay, so why is that TF of QI and D? What is TF? Term frequency. Okay, the number of times that word appeared in document D divided by the length of the document. This is what we call maximum likelihood estimate. Okay, that's the estimate that will make the probability of observing this term the highest. Maximum likelihood estimate. And that's the intuitive way. If we look at the document, how many times this word appeared, then the probability of observing it will be the frequency of the word divided by the length of the document. Okay, so we call it the maximum likelihood probability of QI given the model of the document. Any questions so far? Does that mean that we are done? Did we get what we want to compute the probabilities that we want? Yes, right? This is general, right? For any query term, I can compute the maximum likelihood estimate and then multiply them. Khalas, then this is the probability of what? Probability of the query given the document. But they are not equal. They are rank equal, not exactly equal. Yes, because they are equivalent in ranking. Yes. Okay. So if we plug this in, now we have the multiplication of the maximum likelihood estimates, which is the term frequency of QI in D divided by the length of document. And why do we have this? That's if the query term appeared more than once. Okay. That's now the maximum likelihood estimate of the query given the model. Any questions so far? Right. This formula is problematic, and we'll see why very soon. Let's say that I have this document now. So this is an example. Let's say that I have this document, and now I want to compute this probability given the language model of that document, given the formula that we just studied. Okay, so that means that it will be probability of, so given this probability now, this will be equal to what? The first one is red, right? So red times what? P of yellow times P of red again times P of blue. That's only because we are using unigram language model or QLM. QLM based on query likelihood model based on the unigram language model. Okay, type. That's why we have here P of red twice. I mean square. Type. What are the numbers? Bashir. 4/9 square times 2/9. What do we call this? This is the maximum likelihood estimate of observing yellow in the document, in the language model of the document, times 3/9. Okay, this is what we did, by the way, earlier, exactly. But now it is principle. Now we know why we did that. Okay. Type. How about this one? Can you tell me what will be the probability here? 0. Why? Green didn't appear in the document. So what is the maximum likelihood estimate of green given the language model? 0. Type. That means that this whole probability will be 0. Is that good or bad? Why is it bad? Why is it bad? Or do you think it's good? What do you mean by you need the other term? The probability of seeing this sequence from the language model is 0 because green have never appeared in the document. Fine, but the probability of all of them together, it's not the probability of each one separately, right? So we want to compute the probability of this sequence. So this is the probability of generating this sequence from the language model of that document is 0. That's the meaning of what we did, right? So that means that I cannot generate this sequence from that document, given the model that we have, right? Why is that bad? Huh? Maybe what? How can we know? You mean the term that didn't appear in this document? How can you know also? Huh? Very good. Yes, exactly. It is a big punishment to the entire sentence to give it a score, a probability of 0 just because one term didn't appear in that document, right? Okay, it's like a V2 power. And that term had a V2 power. If the other terms that have a very high probability, it doesn't matter. Because just one term has 0 probability will make the probability of the entire sequence to be 0. Type. Now, mathematically, we understand it. That we don't want it to be 0 because that's, it's like grounding the entire sequence because of just one term. But principally, what is the problem? Why did we get this 0? It looks like we don't want that 0, right? We would be okay with the small probability, but not 0, right? maybe you can think of it that way. But why did we get 0 in the first place? There must be something wrong somewhere, some maybe wrong assumption that led us to get that 0. 0 means what? First, and in this case, what is the meaning of the 0 here? Yes. But the 0 is not only for that term. Now the 0 is for that sequence. Okay? For the whole sequence, right? 0 is the probability of generating that sequence from that document. And that's because the probability of observing that specific term in that document is 0. Okay? Type. Is that correct? That the probability of having this term, just because it didn't appear in the document, it should be 0? Type. Let's get back, I think, 10 minutes or 15 minutes back. Do you remember that when I said that the writer of a document, before he or she wrote the document, had a model in mind, and he made some selection of the words that he wants or she wants to put in the document, and he excluded some of the others, although those words that were excluded might have appeared in the document, right? And still the document will be about the same topic. What does this story mean now? Generally, it means that not every word that should belong to that model appeared in the document itself. There might be a word that didn't appear in the document, but still it belongs to the language model. That means that generally every word in the vocabulary should have a non-zero probability, because there is some, although sometimes might be very small, but there is some probability that the author of the document would have chosen that word. Okay? That will solve the 0 problem, because now I can, if I look at the language model, I will see a non-zero score for every word. I will never see a score of 0. And if that's the case, then I won't be in that problem. Okay? So model will assign 0 probability to unseen terms that didn't appear in the document, and thus we would give a single term a V2 power. Of course, that's not fair. And if you think about what happens in vector space model, for example, in vector space model, what is the ranking, the retrieval model? How do we score the documents? If you remember, that was a summation, right, over term weights. So we have something like TF-IDF, and we sum over TF-IDF scores for every query term, right? What happens if the TF-IDF score for one term is 0? Think about it before you answer. Okay? If I'm using TF-IDF scoring function, okay? If I use TF-IDF scoring function, and one of the terms has 0 TF-IDF weight, what will happen? Will I get 0 from the entire? Why not? Because it's a summation, right? Others might have score, might have non-zero score. The problem is that we have multiplication, right? So 1 0 will destroy the entire thing. But in vector space model, we don't have this problem because it's a summation. Okay. But here it is multiplication, so we have this problem. So the better way, of course, is what we call smoothing. So that's the idea of giving non-zero score for every term in the vocabulary. How do we do that? Let's assume that without doing this, there are, of course, the words that are unseen, the words that didn't appear in the document, we call them unseen, okay, or unobserved. these words, if we just use the maximum likelihood estimates, we'll get 0, right? If the x-axis now are the terms, okay, and the y-axis is the maximum likelihood estimate for that term. So the words that are unseen all have 0 score. So all starting from here until the end of the vocabulary list, all of these words have 0 probability. Okay, few words have non-zero probabilities, right? This one, this one, this one, all of these. Okay, some of these have high probability and some of these have lower probabilities. Okay, so that's the language model if we only use the maximum likelihood estimates, which is problematic as we saw, right? Because any query that has any of these terms, and there are many by the way, any query that has any of these terms, if we use that, if we computed the probability of generating this query, it would be 0, right? Because all of these probabilities are zeros, right? Are you with me so far? Any questions so far? We didn't say how we will get over this problem yet. Any questions so far? Okay. Now we will do what we call smoothing. Let me first ask you a question. What is the total probability here? 1. Why is that? Yeah, because it's a distribution, probability distribution over all terms. All of these have zeros, so the sum of the probabilities here is 1, right? Right. The idea that we said earlier is that we want to give some non-zero probabilities for the unseen words, right? Right? If we do that, of course, this sum, because the overall probability at the end should be 1, right? So we cannot just give some probability mass here without taking it from the other side. So these probabilities have to change also. Actually, most of them will decrease because we will take part of the probability distribution, give it to the unseen words, so that the total still will be 1. Okay? If you didn't get it, look at this. Now, let's assume that this is the new probabilities for the terms. Okay? So we took some of the probabilities for these terms, and now these probabilities are not zeros. If you look at the curve, right? If you look at the curve now, the curve is not 0 here, right? So we are given some of the probabilities to some of these unseen words, and that's of course on the expense of the probabilities of the seen words. Okay? So now the total probability under this curve should still be 1, because we took some of this and we added here. Okay? This is conceptually called smoothing, because actually it is doing something like smoothing the curve. This curve was not smooth, right? But now we will smooth it a bit, okay, by decreasing the probabilities somehow of the seen words and increasing the probabilities for unseen words. How exactly we will do that, we will discuss it. Okay, but that's the idea. Okay, is this clear? Is it clear why it's called smoothing? Who's talking? Mm-hmm. Exactly. Very small value for all. It doesn't have to be exactly the same, by the way, but there will be very small values, but no term will left behind. Okay? Every term will have a non-zero score. So that means that the smoothing technique that we will use will have to make sure that no terms will have a zero score after smoothing. By the way, there are many ways of smoothing. We will inshallah study two today and in the course in general, but there are so many ways of doing this smoothing. But this is the general idea. Take part of the probability mass from the seen words and give it to the unseen words. Okay, I think this is what we already discussed. By the way, the problem of the zero score problem, sometimes called data sparsity problem. It is rooted. The root of the problem is that the words that appear in the document are sparse. They are not representing everything that can be said in the topic of that document. Okay? So the idea of smoothing is to lower or discount the probability estimates for words that are seen and assign that leftover probability to the estimates of the words that are unseen. Okay. Now we'll study the first smoothing technique called Gellinic smoothing. How do we do the smoothing here? This is what we computed so far. This is the maximum likelihood estimate. So that's the original estimate. Okay? So we'll start with the original estimates for all words. Of course, many will have zeros and some will not have zeros. The ones that are observed, seen, will not have zeros. Okay? Now we will multiply all of these probabilities by 1 minus lambda. Lambda is a parameter. Okay? Parameter between 0 and 1. Let's say that lambda is 0.1. Okay? So we multiply all of these probabilities by 0.9. Now the total of the new probabilities is 0.9, of course, right? Because the total was 1. Now we multiplied everything by 0.9. So the total is 0.9. What is left? 0.1. That 0.1 will be distributed over all the words. Okay? How? It will be distributed based on how the word appeared in the collection as a whole. Okay? So this term is the maximum likelihood estimate of the query term in the model of the document. Okay? Now we will mix that. That's why this model, by the way, is called mixture model, because it mixes two language models. It mixes the language model of the document and the language model of the collection. So the remaining part of the probability will be based on how frequent the query appeared in the collection as a whole. Not the query term. I mean, the word appeared in the collection as a whole. Okay? So we multiply the original probability by 1 minus lambda. All of them will be multiplied by 1 minus lambda. So the rest, the remaining will be lambda. Now, how can we distribute this lambda part of the probability mass over all? It will be relative to the maximum likelihood estimate of observing the query term, but using the model of the collection, not the model of the document. What do you mean by the model of the collection? It's like we put all documents of the collection in one document and then estimate the model, the language model format. Exactly like we did in the document. Okay? That means that the maximum likelihood estimate of the query term given the collection model will be the collection term frequency. The collection frequency, if you remember, collection frequency is the total of the term frequencies in all documents, right? So if I put all documents in one document, we call it the collection now. So how many times we saw this word in that new document over the length of that document. The length of that document is this factor, which is the total length of all documents in the collection. Okay? So if a term appears a lot in the collection, then it should get higher probability, higher portion of this lambda part. Okay, so this is like we are mixing two language models. The document language model, we call it the foreground language model, and this is the background language model. Okay, so there are two models here. There is a model for the document, and there is a model for the entire collection. The document, the words that appear in the document, the seen words, we will get their probability as a mixture of both. 1 minus lambda from the document, lambda from the collection. How about the unseen words? The probability from the foreground model is 0, right? Because they are unseen. So they will only get from the collection. Sorry? Unseen in the entire collection. If it's unseen in the entire collection, then it deserves to get a 0. By the way, we will talk about that at the end of the lecture. That's a special case. But if you think about this, this means that this is a completely new word that have never appeared in any of in the web, for example. Can you imagine a word that اختراعه? Okay? It can happen, by the way. Okay? It can happen, and we'll deal with that later, inshallah. But for now, assume that this, if that happened, then this query deserves to get a 0 for yes. Smoothing is done online. What do you think? Why? Do you mean computing the score? Of course, the overall score will be done online, and that's usual, right? And given the query, we'll score the documents online. But these estimates, should we do it online? Do we have to do it online? These are the language models. We can do them offline for every term in the collection in advance. And why should I wait for the Qatar University, the classical query that we have in this course? Why should I wait for it until I compute already the probability of Qatar given every document and the probability of Qatar given the entire collection? Nothing will prevent me. But the exact score, I will get it, of course, online when I get the query. Although, by the way, I can even compute it. Actually, I can compute the whole thing offline. I can compute this completely offline. But the query has multiple terms. I have to multiply these online. But this entire computation, it can be done, of course, offline. I don't need to wait for anything. Was that your question? Yeah. Yes. In what? Can you raise your voice, please? Yes, lower score, but it will not be 0 because of just one unseen word. Why? Why do you think this will be high? Actually, this will be very small probabilities. Why is that? Because this collection is huge. Yes? Yes, based on this retrieval model, yes. But remember, okay? Remember, there is also part in the document. Yeah, there are two components here. That's why it's mixture of two models. It's actually linear interpolation if you look at it. It's 1 minus lambda and lambda. It's linear interpolation between two language models. One that is document, that's the document that we want to score, and one that's the background model that is the entire collection. So even if you get higher, You will never get very high score from the collection model because the collection is huge. You assume that you have a big collection, right? So the collection, if you put all documents in one document and look at the probability of every word, it would be very, very small. Yeah, two words that are in the background, then the one that appear more will have higher score, yes. We should also, yes, we'll handle that later, but yes, we should, okay? Yes, we should. But she's talking about two unseen words. Yes. Why? It's a parameter. Because we have to make sure that the probabilities at the end will sum to 1. Okay, so lambda is between 0 and 1. If it's 0.5, then I give a weight, equal weight to the background model and the foreground model. Okay, but I have to mix both so that I can make sure that the total at the end is 1. But lambda is a parameter that the designer should choose. So now the estimate of the unseen word will be just the second part, the right part, which is based on the background model, and the estimate for the observed words or the seen words is the whole thing. Okay? Yes. What do you mean by part? Yes. As part of the collection, yes, but they are different the language models, of course. Yeah. You mean it contribute, but it contribute one among millions of documents. Other questions? We still have time till Fajr, inshallah. Ihab, where are your questions? No questions? No? Huh? He prefers what? Is that clear? Yes. Who is talking? Mariam, you want to stay to Fajr or the... go ahead. Go ahead. No. Remember that we will score every document and we rank based on the probabilities at the end. So these documents will get non-zero score. You are upset that they will not get 0, but we don't care about them because they will be very low in the ranked list anyway. We hope at least that they will be very low. Okay. Any other questions? But the why we do the smoothing here, or why the smoothing is good, because maybe we have a document that has a query has 5 words, 4 of them appear in the document, and 1 didn't. If we didn't do that smoothing, this document will get 0 score. So that's a huge disadvantage. Okay? Use the Boolean if you want. Use the AND if you want. Okay. Okay. Now, what happens if lambda is very low, very very low? Toba? Huh? Will be based on would it be very low? Okay, look at the equation here and tell me what happens if lambda is very small, very, very small. Close to 0. What happens, Ahlam? No, say it again. The unseen words. Yes. Yes, almost 0. Type. What does that mean? Yeah, the background is disabled. When lambda is very, very small, it's like background is disabled, and now we are back to the foreground only. Type. For a document to have a non-zero score, what should it have? Now, and if I ignored completely the background model, if lambda is very small, it's like completely disabled, right? We only depend on the foreground now. Now that means that if a word is unseen, it's almost getting 0, right? Type. That means that the documents that will get a non-zero score are the documents that have all the words. Very good. Or at least most of the words. Yes. So that will be like ending. Okay. Type. What happens if we have a high value of lambda? Very high value of lambda. Yes. Yes, the background will dominate. Okay, the background will dominate, and what happens, and the foreground almost is disabled. Okay, so say it again, sorry. Yes. We'll get a non-zero score. We'll get higher score. Yes. So it's like all. Yes, it will be like all in this case. Right? And this is good for long queries. Because long queries, I want to really, because there's a very low chance that a document will have all the words, right? So I might need some ORing concept or notion in the query. Okay, and of course there is here we are talking about low value and high value, but there is a range between 0 and 1, right? So understanding the meaning of the value of lambda as it increases and as it decreases will let you understand the behavior of that retrieval model. Okay, so as it goes to close to 0, it's like ending. As it goes close to 1, it's like all. Yes. What do you mean by us? Who are as the designer of the search engine? Yes, this is like a knob that we can tune. Okay, of course the user doesn't see it. Yes. Any other questions? No, we are just saying that lambda doesn't depend on anything. It's a free parameter that you can choose between 0 and 1, of course. But we are saying that if you choose lambda to be high, in other words, if your context requires long queries, then high value of lambda should be better. Challenge of what? To whom? Yes, of course. It's not a challenge. It's a decision. He has to make a decision. And yes. And how can we make a decision on that? Experiments. By doing experiments, right? And evaluating the performance of the system using different values of lambda, right? How can we do the evaluation? in our eye using test collections. Everything is connected. We are doing everything for a purpose. Question. Yes, Muhammad?
Has there been any interest in finding what happens when lambda equals to half? I'm kind of curious what's between
No.
and or.
I don't recall from the literature that there is something unique for that. No, I don't have an answer for that.
Oh, thank you.
Okay, so correctly setting lambda is important, of course, for good performance. Don't just put it randomly any number. Now, if you want to plug this in, then the retrieval model now, or retrieval score, will be the multiplication of this for all query terms, right? Remember that the original formula, that was the multiplication of all words, يا واثق, right? Until you are looking at the slides. يعني انت مش عاجبك كل البورد دي. مو بتبص اللابتوب عندك. اوكي. طيب. بعدين يعني خلي في تعاطف مع الناس اللي هي مش لاقيه السلايدز لسه يعني. لقيتها؟ حد بعتها لك؟ طيب. Any questions so far? So do you know how we got this? Okay. Here's a quick example. Animation is sorry, it's very bad today. طيب يعني I will leave you with this example then if I cannot hide the answer. So the question here was that we have a collection of two documents and we have a query and we want to rank these documents based on the query. Okay, so what you want to do is to compute the probability of generating the query given the document, given the language model of the document. Okay, so here we assume maybe we heard Muhammad talking about lambda equals half. So the example here is lambda equals half, and we want to estimate, to rank them, we need to estimate the probability of the query given each of them. Okay, so what we will do is to compute the probability of every query term given the document. So can you justify, please, someone can justify to me why we have these numbers here? Marina? Sorry? Yes, Michael? What happened to Michael? It didn't appear in document 1? Yes, so that's 0 here. Because that's the foreground or the background? The foreground model, 0 because it didn't appear here. Okay, why is it 1 over 18? Is it Jackson or we are still Michael? So this part is for Michael, this part for Jackson. Yeah, so that's the background probability. Why is it 1 over 18? Yeah, Umama. Yes, so the number of terms in the entire collection is 18. And why is it 1? Yeah, because Michael appeared just once overall. For Jackson, it appeared once in document 1. And what is 11? The length of document 1. Okay, and why is that 2? Yeah, Jackson appeared twice here. Once, twice. Okay, so you can do the same also for document 2. And if that's the case, then document 2 seems to be more relevant than, I mean, it will be ranked higher than document 1. Any question about how we calculate these probabilities? Yes. Lambda is, yes. Yeah, lambda is half, that's why we multiply by half both. If lambda was not half, we would have multiplied it in each side. Yes. By the way, good that you remind me. The terminology that I'm using in the slides is a bit different than the textbook. Please stick to what I have in the slides. Okay? I think the textbook is the opposite. It's lambda with the foreground and 1 minus lambda for the background. Just stick with that. Any question about this? Okay. The other, I told you that we will study two smoothing techniques. So the first one is called Gellinic Mercer, which is the mixture model, with the linear interpolation between the foreground and background. In the other method, which is called the Retrieval smoothing, here we use the notion of what we call pseudo counts. So we assume that the document shouldn't be of length like that, the cardinality of D, the length of D, shouldn't be only, the length of the document should not be only what we observe, but we will add a constant number of terms, like virtual, we call them pseudo counts, pseudo terms, to the document. Okay, so let's assume that mu here is a parameter. So mu, let's assume that mu is 100. So it's like we will add 100, it's like we see 100 more terms in every document. And these 100 terms will be distributed between all the vocabulary in the collection. Okay? So if we are talking about a specific term, it appeared TF times plus mu times the background probability. And let's say that it appeared 0.00001 in the collection. So we multiply 0.00001 by the mu, which is the pseudo counts, the 100, just to give it a portion of this 100. Okay? Now, the numerator is like what is the new term frequency for that term. It has two parts. Part from the actual observations, which is the term frequency part, plus the pseudo counts. Pseudo counts are distributed over all the words based on how they appeared in the collection. Similar concept to Gellinic Mercer, but it's implemented in a different way. Okay? Is this clear? واضح. Is this clear? مش فاهم معناه ايه. Okay. So mu is constant. Okay? How do we interpret mu? Mu is like how many terms we will assume they should appear in the document over what we already observed. Okay? Usually this is in hundreds or thousands. Okay? Let's say that's 1,000. So it's like we will add virtually 1,000 terms to every document. Now these 1,000 terms, they are not exactly 1,000 terms, but they are 1,000 counts, 1,000 observations. Okay? But actually when we distribute them, we distribute even portions of them. Yani one term can get 0.5 and the other will get 0.3. Right? Because we will distribute them among the entire vocabulary set, not just 1,000 terms. Okay? Type. Now, how can we distribute them? We distribute them based on their background probabilities. If a term appears a lot in the collection as a whole, then it will get higher portion of this 1,000 pseudo counts. Okay? Is the idea clear now? In this 1,000, yes, exactly. Okay? Each one will get how many, what portion is based on the background. That's why we multiply mu by the background probability. And we divide now by the length, the original length of the document plus mu. Why? Because we assume that the total pseudo counts will be mu. Okay? And that's the portion for what? Yeah, this is the portion among mu that is assigned to this specific term. Okay, remember this is the probability of Qi, that one term given the model. Okay. So adding and distributing pseudo counts over all terms in the vocabulary. Yes. Very good. Now let's assume that Qi appeared in the didn't appear in the document. What will be the probability for it? The foreground, the T. No. Okay. Let's look at this and see what will happen. Okay. What is TF of Qi and D in this case? Ahlam. 0. Very good. So that will be 0. Mu is a constant. Is given. Okay. What is this? That's the background probability, right? We can compute it. So that will not be 0 unless the term is didn't appear in the entire collection. Okay? But it shouldn't be 0. And how about the denominator? That's the length of the document, and that's mu, that's a constant. So it will get non-zero score. But only from the part of the background probability. But this is considered like the foreground. Okay? But they are not seen as in Gellinic Mercer, it's mixture. Actually, we'll see it, but it's not exactly like Gellinic Mercer. Okay, so if we distribute, you have any question first before we continue? Right. If we look at this formula and we just distribute the two factors in the numerator apart, okay, so we'll have TF over the length of the document plus mu. TF over the length of the document plus mu. Here we just multiplied by the length of the document and divided by the length of the document. So we didn't change anything. Okay? With me? Plus this part times the background probability. So this is mu over the length of document plus mu times the background probability. Now this looks like what? Gellinic Mercer, right? If we, what is this now? That's the foreground probability. This is like lambda, but it's not. Okay? It's like lambda. Okay? So now we can see it that way. Actually, that should be, it's the same. That should be the foreground probability, which is P of, I think this is next one. Yeah. Okay, so that's redundant. This is the one. So that's, now it's like a factor multiplied by the foreground probability times, actually 1 minus the factor. If you look at it, these two, the sum of this is 1. Very similar to lambda and 1 minus lambda, right? And that's the background probability. Type. Why is this different then? It looks like exactly this, not exactly the same, but looks like very similar. Now, look at these factors. Okay, this is corresponding. If we look at, so this is the Schlee. If we look at Gellinic Mercer, this is corresponding to 1 minus lambda, and this is corresponding to lambda. The basic difference here is that in Gellinic Mercer, we said that lambda and 1 minus lambda are constants. They don't depend on anything. Look at now these factors in the Schlee smoothing. They are a function of what? Of the document length. So this is like mixturing, but depending on the document. Every document will have its own mixture. In Gellinic Mercer, the mixture is constant. 30%, 70%. 30% foreground, 70% foreground, background for all documents. Here it's different. It depends on the length of the document. Okay? That makes it, of course, different. Dynamic, exactly. Yeah. It depends on. It depends on the. I don't want to get the updates. What should I do? Okay. Is that clear? Any questions about this? Sorry? Oh, of course, yes, both are used, yes. Yes. By the way, if you look at the Gellinic Smoothing here, if the document is long, what is the effect of having a long document here? You know, look at the formula and tell me. If the document is long, what happens? The focus will be on the foreground. Why? Yeah, because if the document is long, it means that the numerator will be very close to the denominator, which means that the mixture will go will have higher weight towards the foreground model and much lower weight for the background. And I hope that now you understand what we mean by the mixture model, right? How much probability you will get from the foreground, which is the document dependent, and how much left to get from the background. But remember, the seen words will get from both. The unseen will get only from the background, but the seen will get from both. Okay, these are just very quick notes on all of what we discussed. By the way, is called query likelihood model. Okay, so generally it has very similar effectiveness to BM25. It was shown that in the literature, even with more sophisticated techniques like topic models that we would not discuss in that course, but with more sophisticated techniques, language models actually sometimes outperforms BM25. And as I said earlier, there are several alternative smoothing techniques. These are just two. There are papers that survey the different smoothing techniques. One final note. What we studied in this lecture is, as we said earlier, it's called unigram language model. Okay? There are, of course, general language models. We can use bigram, trigram, stochastic. Okay, so these are generally called n-gram language models. As we higher the order, the quality of the model is, of course, will be better because now we are observing dependency between the terms, but we need to estimate much higher number of parameters. Okay. So in this course, we'll only, or at least in this lecture, we only focused on unigram language models. And I want also to end with this. Language models of IR, there are three possibilities. We can estimate the probability of generating the query from the document. And that's what we studied today, right? Right? There is also probability of generating the document based on the model that is estimated about the query. That's the opposite. So we estimated the probability of generating the query from the document, right? Type. There is another approach, also language modeling based, that do the opposite, that tries to see what is the probability of observing that of getting or generating that query from the language model. What is the probability of observing that document from the language model of the query, which is the opposite of what we did. And there is also language models that use both. Of course, we only studied this. I just want to put you in the context of the entire literature of language models. So we only use the unigram language models among the different ways, and we only used one approach out of three approaches of language models, which is generating the query, the model that generates the query from the document. The last one, there are models that use both, that compare actually both. Uses both approaches together, mixing. Yeah. So estimating the relevance probability from estimating the probability of generating the query from the document and the document from the query. We will not discuss this.